Hello everyone and welcome to this new video. Today will be the third lecture, and to be more specific, we will head further into how we can do the FEN extraction in C++ code. So without further ado, let's head right into it. As I already mentioned in the intro, we will have the third lecture today. So what have we done in the past? We already know how the basics and Stockfish work now. So we had a quick overview over the Unreal Engine, and we know how to use Stockfish now. So today's lecture will be about how can we implement the FEN extraction into our C++ console program, which we will then create in the next lecture to be also interactive. So just as a quick recap, what are FEN strings exactly? We have on the left side how a game looks like when you pick as the first move G4. And as you can see, it's quite difficult to manually capture the board state. That's where FEN strings come into play. And they look like this. In the mid, you can see a standard FEN string. I will move my camera out of the way quickly. And it's including the board state, the current color, castling options, or passant, half moves, and full moves. So far, so good. We already know that. But what we don't know yet are the exact parts of this FEN string. So the board state actually offers a lot more information than you can see on the first side. As you can see, we have upper and lowercase letters in there, and white equals uppercase in this case, and lowercase is black. So the letters also contain information which piece is sitting at which position. So P equals pawn, R is the rook, N is used for the knight, B is the bishop, Q is queen, K is king, and that's all 6 options we have on the field. You can see there are also slashes inside the string, and that's simply the rows. So the slashes split the rows from each other, where that's why we have 8 rows in total. And then there are also numbers in it. And because it can get a little tricky from here, when you don't have a graphical interface in front of you, I just wanted to show this to you on chess.com. They actually did an excellent job in explaining how it works, and let's have a look at the first line here. We have the rook, the bishop, the king, and the rook. And as you can see, they are spaced a little bit between each other. So we have the rook, 1 empty field, the bishop, the king, and then 3 empty fields, and then the rook. When we also now take the color into place, it looks a little bit different because we have now a pawn here, another pawn, then a white bishop, a black pawn, a white horse, white knight, and a black pawn once more. So as you can see, we have the black pawn, we have 2 empty fields, we have the black pawn, we have the white bishop, we have a black pawn, we have the white knight, and then we have the black pawn. So I guess you can see already where this is coming from and why those numbers are so useful, and a FEN string is not that hard to understand once you managed to wrap your head around the fact that the empty fields are just numbers and you only have 6 other options, uppercase and lowercase, for the chess pieces on it. Right, back onto the slide. We can also determine the current color, which is shown by a small or lowercase w for white or a lowercase b for black. And that's it basically. So you only have the current color and you can decide it whether there is a w or a b inside the string. Then the castling is a little bit different. We can castle either kingside or queenside, and there are several things that allow us to do so. One thing is that we haven't touched the rook on the according side. So on the king side, the rook on the right or the left, it depends which color you are, mustn't be touched before, and the king is not allowed to be moved before, then you are still able to castle. What you can see here is that both sides are still able to castle on both sides, so both king and queenside is allowed here for both colors. Right. Then we have the or parser. And the or parser can either be a minus inside the string or, for example, B3. How can this happen? So if we have a minus, there is no or parser possible. But if we have, for example, B3 here, the field where an or parser can happen is set to B3. So that requires a few conditions to be able to capture your opponent's pawn. And it is one pawn must have advanced 2 fields. Let me move out of here. Which is only possible when the pawn was still on the standard square before, and the square between the standard square and the current pawn's position is then marked as the or parser square. So if an opponent's pawn is now located in a way that he can reach the or parser square by moving one step diagonally, the pawn can be captured. And which is really, really important, it's only allowed for this specific move. If he moves with another chess piece than this pawn, the or parser is not possible anymore. Okay. I know this is quite tricky, so let's go back to chess.com to explain it a little better. And you can see what I mean here. So watch my mouse cursor. We have this pawn advancing 2 forward, and it was still on its standard square before. So when this pawn would be located around here, it could reach the or parser square going diagonally. Also, this pawn, if it would be here, it would reach it. And what happens then is a little bit confusing on first sight, because you are able to go this diagonal way, and this pawn simply disappears. So you actually captured it. And as I mentioned, this is only possible for one move, and only when the other person moved the chess piece in the exact same way as here. And the or parser square is colored red here, so you actually also know where this would be inside the FEN string. Well, since I understand that it is quite complicated to understand it when you don't have the graphical part, I just moved to chess.com once more, and now we can go back to the slides, and you can see there are another few things we can capture. So the half moves are needed to determine whether a possible draw is inside. So that means how many moves were made without a pawn advance or piece capture. And if this counter reaches 100, a draw can be offered. And that counts for both white and black at the same time. So keep that in mind. The full moves instead are just incremented when both white and black have done their moves, and it can only get incremented by 1. And there is no other function. So now we know exactly how the FEN extraction works and what we can actually extract from the FEN string in total. All right, now that we know exactly which parts are located inside the FEN string, we can go on with the FEN extraction. And as I already told you, we have only 3 relevant files for us and the according functions to them. Last time we had a look at the Chess AI handler, how we can get our requests to Stockfish and what can we receive as an answer from there. And today we're going to do the FEN parser. To be specific, we will implement the method parseFEN, which parses a FEN string and extracts every part individually. Then we have the next lesson, which will be console chess program. So we have the whole working program from there. Well, see you in Visual Studio. If you don't know how to implement the project and how to actually set it up to work with it, just have a quick look at the last video where I explained exactly how to do that. There are also timestamps in the description for each of the videos I make, so feel free to skip through the video and just have a look at the important parts for you. Right, as you can see on the right side here, we have the files listed already in our project, and the file we will have a look at now will be FEN-Parser.cpp. You can see there is already a castling availability implemented, and we have here the parse fen string, which currently looks a little bit like there's nothing in it. We already know that we can enter a fen string into there, and we'll receive a board, which is a vector using strings inside of it as the board state. Then a bool variable, which is the turned color, so whether it's white or black. Then we have the castling rights, so this will be also a vector of booleans, and those castling rights will just include, if it's possible, to castle on one side or the other, just as you have seen in the fen string already. Then we have the string or parser target and the half move clock and full move number. Well, you might wonder why I know that the fen string is an input and the others are just outputs. That's visible with the keyword const here. So when we put a const in front of it, it will be used as an input because it's not changed. And if we don't put a const in front of it, it will always be used as an input and an output. So we have to provide it actually. Good. What you can see now is that there is a console output which tells us parse fen not implemented yet. And from here, we have to look a little bit back to understand why and how we can call parse fen. So if we go back to our chessai handler.cpp, which is using Stockfish to request it with a certain skill level and fen string, we will get the extract response. And this extract response is written in here. So we have already included a fen parser, and we have the method FEN-Parser.extract-FEN-Details. And as you can see, there's nothing there yet, except for we have our parse fen in here, and we create a lot of local variables which are used as the output to work with the function parse fen. We also have the detection of possible castling moves, and we can detect all parsers with it. And we can also see whether draws are favorable or not, and that's quite easy once we have the half move clock counter and it is bigger or equal to 100, then the draw can be offered based on the half move clock. Good. Now that we know where parse fen is used in, we can go back to it. But that's just as I said, fen is only used as an input and all the others will be used as an input and an output, so we have to declare them before usage. Let's go back to parse fen and let's start with the fen parser. So our task is quite clear here, right? We have to split up this fen string into its 6 components, and we just have to find out how we do it best. So when you have a task like this, it's always best to find a so-called delimiter to determine how you want to split it up. And what becomes very, very clear once we have a look at the string here is that we have a total complete string until here. Then we have a space, another space, one more space, and so on. So we can use the space as a delimiter here. And that makes it quite easy for us because in code, we now have to just iterate over the string, which currently looks for you like this. But I already have the implemented version here, so we can have a look at that. And you can see I haven't changed anything except for a few variables here. And those variables will be explained in a second. So first of all, we have to split the fen into parts using spaces as delimiters. We can use a while loop here because we just iterate over it until we get no more string, and the getLine function of the standard library. So what does the standard library getLine do for us? As you can see, we have to put a so-called input stream or iStream into there. Then we have to put a string ourselves how we want to name this part of it. And then we have to place a delimiter, so to determine when to split up the string and when not. So in this case, I have implemented a FEN stream. You can see it's a std iString stream because we use a string here. And it's a FEN stream consisting of strings. And I'm just using this right here because I already implemented a string that's called FEN string and gave it the according FEN string, which will be passed into the function. Right, now if we iterate over the string, it will be split up at each space and it will be put in a part or a string, which we call part, and then we push it back into a vector string so we can store it efficiently. So how does this work now? Just imagine we have this getLine, string stream, and so on, and then we push back any part we receive here into the vector. So now we should have 6 parts into the vector, and that's exactly what happens next. We check if there are not 6 parts, something must be wrong. So we just use the default FEN string. Otherwise, we do nothing because, of course, it's already done correctly. So how does this error function work, I'd say? When we don't have 6 parts, we just construct it from this FEN string here. So we clear the FEN stream to be able to put something into it once more. Then we initialize it once more. We clear also the parts array, and then we use the FEN stream once more to create the parts from it. Why is this necessary? Imagine someone puts a wrong FEN string in here, and we just don't check it. If we don't check the correct length and also its parts, we will end up with a very, very confusing part or split up or whatever. So just in case someone messed this up, we provide the option for him here to not pass a correct FEN stream, and we will still be able to use it using the standard FEN string instead then. Right, the next part is to split the board FEN into rows. So what is board FEN? Board FEN is in this case the board state, so all of the red parts here. And what can we use to split it up? You might have already guessed it correctly. It's the slash here. So we just use this as one part, and we can split it up into several parts, when we use the slashes to split it up. All right. Here we go again. Wrong part. Here we are. Okay. So we just create a new iString stream called row streams and hand it the parts 0. As we saw already, that's the red part in our presentation. Then we create a new vector string array that's called rows, which is able to store the rows on the board. And now we just do the same as before. We also create a while loop, and this while loop iterates this time over the row stream, just takes the part out of it, and our delimiter, as I mentioned already, is a slash here instead of a space, and that's how we can push back the rows. So all the rows are pushed into the vector now, and maybe some of you might ask why I haven't used an array here. You could also use a normal array, but normal arrays have the problem that you don't have unlimited storage. So you have to determine, for example, that you want to put 8 parts into it, and you can't put more into them or less into them. In this case, it would work, but I'm a friend of procedural programming, so I just used a vector string, which can be unlimited long, can contain unlimited strings inside of it, and I can just push it back anytime I need to do that. So as a quick summary, a vector is just basically an array with unlimited length. So you can use it more procedural and will never have the problem of something like RAM overflow or something like this. Right. Back to the rows. We can now convert the FEN rows to the board representation. So how can we do that? When we have a look at the presentation once more, we can see this one is now a row part, right? And this row part can now be used to be split up into separate characters. So what can we use it as a delimiter here? Sadly, there is none. So we just use positioning. We just use this one as number 0, 1, 2, 3, 4, 5, 6, 7, and so on. And that's how we iterate through this board state. If we go back to the console chess, it looks like this. So we just iterate through the number of rows. We have 8 rows, so let's back to the FEN string. 1, 2, 3, 4, 5, 6, 7, 8, right? And then we go back into the program, and now we can iterate over its characters. So now we are into the row, and first of all, we check whether or not, no, I have to put that a little bit different. So now we iterate over the chars in the row. So once more, we just iterate over here. So this is the 0, 1, 2, 3, and so on. All right. From there, we have to check whether we have a digit in front of us or a letter. So we just use isDigit, which just needs to have an integer parsed to it. And this is our current FEN char. So for example, an R would not be seen as a digit, so we end up in here and just push back the board, the current FEN char to the board. All right. Then if we have a digit here, it represents an empty square, as we mentioned before. The empty squares is then, and this one is a little tricky, I know there are better ways, but not in C++, how to convert a character to a number. Normally you would use a string to int or something like that, but there is none such function in C++ here. So we just create a new string and subtract it from our current FEN char. It works because we made sure before that we have a digit. So we can actually use, for example, 1 minus 0, and it works, and we get a 1 back. So from here, we can just iterate over the empty squares we get out of there. So for example, we have a 7, which is 7 empty squares. And then we just iterate from there and push back a dot to the board state. And a dot in our case just means an empty square on the board. Why a dot? It's just easy to distinguish between a dot and a space, for example. So when you use a space here, it can be a little bit confusing because it could also be an error. But in this case, if you see a dot, you already know, okay, it's an empty square. I'm sure about that. Well, and if we don't have a digit, we just push back the character and that's it. So we just created our board. Well, the other parts are whether or not it's a white's turn. We just check if parts 1, so in our case, in this presentation, the current color here, equals W. If yes, it's the white's turn. If not, it's black's turn. Castling rights is then parts 2. So once more, this is 0, 1, 2. Here is 2. And we can just check whether or not this parts contain a castling availability. And this is also a function which is not written from the beginning. So how can we check if there are castling rights in there? You might have already seen it, it's down here, but I just want you to think about it very quickly. So this is the string we have to look out for. And now how can we convert that to a Boolean? All right, the answer is fairly simple. We just parse the parts towards the function to the get castling availability. And we create an empty vector of booleans, which is called castling availability, and everything in there is false. So our first position, so in this case the 0, will be true if we find a uppercase K inside of the string. What you can see here is, first of all, the assignment to the array position. And on this side, you can see something different. And what might confuse you is std string endpos. That simply means you would receive string endpos if it's not inside the array. So if we just check that it's not an endpos in there, we can ensure it's in there. Quite confusing, I know, but just put it like this. If a uppercase K is in there, it will be true. Otherwise, it will be false. Same for all the others, except for the different positions inside the array. And then we just return the castling availability. So now we get a vector out of there with 4 booleans contained in it, and we actually know if black or white is still able to castle and which direction they are. Then we have the parser target. That's simply part 3. So back to here, part 3, the minus in this case. And then we go on with the half move clock, which is something I have to explain first. String to integer, so stowy, means that you simply convert an integer to, no, sorry, a string to an integer. Since we only have strings in here, we have to convert that to the right number to then be able to check it out. All right, so we just use parts 4 in there to determine the half move clock. And the same with the full move number. It's also a string currently, so we have to convert it to an integer, and then we can push it back into the full move number variable. All right, now that you've seen how it works, I just want to show you once more how we use it in the chessai handler.cpp. And you can see it's here inside the extract fen details. So we just parsed the fen and filled up all of these variables in there. What we now have to do is detect for possible castling moves and to detect for all parser. And why this is the case, or why I decided to do it, I will show you in the next part. All right, let's head straight into the last topic for today, the special rules. First, I want to show you why we actually need them, and then I will show you how I implemented them inside the code. So first, what are special rules? We have the promotion, castling, and all parser, which we have to handle. Why do we have to handle that? I mean, it would also work if we don't handle them yet, but it's for later. So, for example, when we have a castling move, we can easily do that in 2D because we can switch to characters quite easily. But what we can't change that easily is when it comes to a 3D environment. So one piece moving against another doesn't work, so we have to move it up first, go over it, and then put it down on the other side. And that's exactly why I implemented those special rule signatures. And the special rule signature simply shows you that the promotion now includes an arrow. So that's for we change a piece against another one. And that can only happen when a pawn reaches the other side. And it can either be promoted to a queen, rook, knight, or bishop. Well, the other part is that Stockfish wouldn't show you that there is a promotion happening because it would just look like A7, A8, and a Q behind it, or an R behind it, or something like this. And just to make sure we can easily detect it inside the code, I added this arrow towards it. The castling would not be distinguishable from other moves because it would simply just show you the left side of the move. So only the king moves and the rook behaves in the other way around to it. So we have one move, the king goes to this side and the rook moves to the other side. And just to ensure that we will be able to capture both moves in a 3D environment, I just simply made it that we have this kind of sign between it, so we can split the two moves, one there, and that contains everything we need to know. We also have to meet certain conditions for it, but you will see it later in the code, or you can click on the link here or any other link like chess.com where this is presented very, very well. Au passant is then shown by a minus and would also not be distinguishable at all, so you would only see a4, b3 in this case, and I decided to put a minus between them because we get rid of a piece, and that will be even trickier in 3D environment because we detect the collisions based on the movement. So we wouldn't touch this piece. And to be still sure, or to still make sure that we get rid of the missing piece, we can move there. And if we save the field we have to destroy the chess piece on, which is b4 in this case, this will get destroyed afterwards. So the chess rules are actually correctly applied. So thus we have to save both the move and the chess piece we have to delete. All right. So how does this look in code now? Can you still hear me? Okay, good. We are in the chess. Here we are back in the console chess.cpp. And as you can see, we have a function here. I'm currently in the main function, and I don't want to spoiler too much about it, but we have a FEN string here, which we start with. And I just created one where we can check how those special rules are applied and how they look in the legal moves. So let's start with this FEN string here. We can just simply swap it. And when we start the console program now, we will first have to enter our name. So our name is Luca in this case. Let's take no test, and I want to start. And as you can see, the whole field is set up correctly already. What you can see here are the special moves for the promotion. So I can either promote my pawn to a queen, rook, bishop, or knight. And I can also castle at the moment. And when I do a certain move, so I can enable an en passant as well, which would be d2, d4 in this case, then my opponent not only has the the promotion abilities, but also the castling ability and also the en passant ability. And as you can see, they are always added behind the string. So when we put in the e4 d3 now, minus d4, then we simply get rid of this piece here and can apply an en passant towards it. All right, the promotion in 2D also is not stunning at all, but yeah, you can see already those are the options we have, and we could just simply do b7, a8 and go with queen, for example. And now there is a queen located at this position. We can make sure that we didn't miss it. Look, here's a rook. Now there's a queen. All right, and that's simply how we can determine which move we want to make and also make sure that everything works correctly. We can now also do castling. So let's do this for a second. h8, f8. All right. And now you can see the rook and the king have changed their places. Same for the other side. e1, g1, h1, f1. So here we have the move. And to make sure that this is not creating any problems within Stockfish, I created a small little function that gets rid of the add-on. So in this case, we check the legal moves here. We put something in there. Then we erase the spaces before and behind it. And if it's now in the legal moves, we check if there is an add-on included. And if there is a arrow included in there, we simply save the promotion move like this. So we have the move and we also know what we should promote it to. And you can see I simply apply it behind each other. So for example, we had B7, A8, B7, A8, so it ends up like this, and it was before something like A7, B7, A8, and then we had this one here. So that's simply what I do, and that's to check whether a promotion is happening or not. All right, the other two parts are simply the castling, which I already mentioned, the sign for, and the minus for the all parser string, which all would look like this, as I already mentioned, for example, E1, G1, and then we have H1, F1, and this would simply look like that afterwards, so Stockfish can handle that. So last part for today is how can we detect the special rules now? I just showed you how we can restructure it, so Stockfish knows how to use it, but we still don't know how we can actually detect it. And you will find out once more that it was not just, let's say, I wanted to make it for you as fun, as easy as possible. So I didn't want you to code all the algorithms you would need to check for promotions, to check for castling, and so on. But I just want to give you a quick overview over it. So the promotion piece check is the easiest one, which you can find in the chessaihandler.cpp. And it's also included in the check for legal moves. So whenever we get a move that's longer than 5 equal or longer than 5 letters, we have a promotion piece. So why is this the case? We have, for example, A7, B8, Q, and that would be the move we get from Stockfish itself. So we can easily determine that it's a promotion move based on the Q behind it. That's unique to all other moves, so you won't find it anywhere else. We can then simply check if the line contains this, so if the line length is bigger or equal to 5, and it contains a Q, R, B, or N on the position 4. So remember 0, 1, 2, 3, and here's the 4. Then we have a promotion. And now we can simply split it up. I just decided to also use to upper and to lower. That's simply based on if it's white's turn or not. And if it's white's turn, we turn it to uppercase. If not, we turn it to lowercase. And then we simply push back the move plus the arrow plus our promotion piece. So it doesn't look like this anymore, but instead it looks like A7, B8, Q. All right, so that's the first part, how we can detect promotion. The other two are a little bit trickier, and they are inside the FEN parser. So when we go to extract FEN details, we see we have parse FEN here, which we already created together. And we have also detect possible castling moves and detect all parser. And the detect possible castling moves includes negative moves and squares under attack. So first of all, I just want to quickly run over this code with you. Don't mind too much the structure of this. It's simply only those moves can happen. So if we find one of those, E1, G1, E1, C1, if we are a white player and we are currently allowed to draw, then we can only take these moves. And if we are a black player, we can only do this one. All right. So with this being said, we check if the castling option is possible. And if castling is still allowed, then we know we have to check the king row and the min column and max column. So what does that mean? Let me show it to you on the website. So this is the king row. You can clearly see that. And it can either be 0 or 7 in our case. And that's a little bit of a tricky situation here because the the column of the king will always be the same. And we have to check all of those fields here if they are empty, and all of those fields as well if we are still allowed to castle onto the other side as well. So same for here. That's what happens in there first. So we determine whether or not we have to go from 5 to 7 or from 1 to 4. Good. Next part is that we check if the square is under attack. And how can we do that? Just have a look at this option here. So we can simply use those squares are under attack because they are under attack from the rooks, and those squares are under attack from the black king. So in this case, we could castle, of course, to this direction. But to make sure that this is not the case, or to check if it's actually possible, we can just reconsider our thinking. And what can we do? We can just check if the square is under attack by checking if any of the negative legal moves, so when we change our perspective to the opponent's perspective, and this square is mentioned at the last part, so we always have something like this, right? A7, B8. So if this includes the target field, includes our position we want to move on, then we are in check and we can't move there anymore. This also is the case for all the other fields on our way. So if we would be in checkmate somehow, in this case, we would not be able to move there, all right? So we first have to check if the whole space between us and the rook is empty. That happens here. And then if none of the squares is under attack. So that's all basically. And then we can just determine whether castling is allowed or not. And if it is allowed, we just remove the string from the vector. So for example, we had something like E1, G1 there, and we just remove that and replace it with this instead, so we can actually determine whether or not we're allowed to castle. Let's just quickly jump into the negative moves. How do we do that? As I mentioned, we just change the perspective. So if we are white, we just set it to black, and that's it. And then we just send the whole FEN string back to the JSAI feedback function, which then will receive a response from Stockfish, so we actually know what legal moves the other person would be able to do at that moment. All right, next part, and that's the last tricky part, is the en passant. So let's keep in mind an en passant can only happen when, for example, in this situation, a black player would be located on one of those two, and it has to be a pawn to be even possible. So that's exactly what we do here. First, we check if an en passant is possible, and that's only the case when we have a field mentioned inside the FEN string. So for example, B3 or something. We can just simply have a look at here. In this case, E3 would be the field which is targeted by the en passant. All right, then we just simply check if for the column letter and the target row, we just change the direction because that's a little bit tricky to understand. I know, but when we open up the console chess and I just enter quickly my credentials once more, no test Luca. Okay, then we can see that the whole field is changed. So this is our row 0 and this is our row 7, which is quite a little bit tricky because you always try to read it from here, but that's just simply because we implemented it like this. And it has also a little bit more of a reason, but just keep in mind that we just flip it so we can think from our perspective again. All right, then we just check if the en passant field is empty. If it's not, an en passant is not possible anymore. And if still an en passant is possible, so no field and a field is mentioned in the FEN string and no chess piece is on this field located, then we just check into which pawn direction we would move. So once more, if we are white, we can only move into this direction here. If we're black, we can only move downwards. So that's what we add there. And that's also why we use the adjacent row for it. Sorry here. The adjacent row simply means that we go from the all parser field and go one step back into the direction where the move happened. So we are now in this field and we only know about this field, so we just check for that field here. All right, and the last part then is to create an all parser move add-on, which is not that hard to understand. It's just simply the target field and or all parser field more, and the field which we want to destroy. So in our case, we just do it by adding the all parser substring plus the adjacent row we just created, which is in this case, for example, here, b3 minus b4. So that's what's actually inside of the all parser move add-on. All right, the last part is that we check for several conditions. So if we would move outside the field when we go one step to the left, because we have to check those two fields, so one step to the left, one step to the right, then we wouldn't check for it. Otherwise, we check for it. So now it's only the case that an all parser is possible when there is a pawn, black pawn located here. And that's what we check for here. So if on this position is a pawn located, then we know we have an all parser and we can just create it by using the starting field, which we create from the column letter and the adjacent row, and the all parser target, which we then use as the all parser move add-on. And we simply remove the string from the vector once more, so we just change the string where no all parser is detectable for us because it looks the same as a normal move into the all parser string I just created. All right, the last part is then that we have the starting field, which is, sorry, the A4 in this case, and the all parser move add-on would be B3 minus B4. That's how we create that string here. The same for the other direction, so we checked only for this now. Now we check also for this, and if there is a pawn located, we just add it to the string, otherwise we don't. I hope this was a little bit delightful for you, so you at least have some clue now how you could be able to detect those specific chess rules. And I think you also got a clear overview why I did not decide to code it together with you, but instead give you the already built code. And those algorithmic parts inside the code are quite exhausting, I know that. And that's one reason more why I don't want to do it together with you. I still hope you got the most out of it as possible, and I really look forward to hear from you. And yeah, that's it for today. We just fulfilled lecture number 3, which was FEN extraction setup. And yeah, thanks for watching. Thanks for your attention. I wish you a good evening. See you next time.